So we talked about the Bohr model of the electron, where I have the nucleus in the center surrounded by electrons in these discrete energy level orbitals. And the Bohr model does some good things. It explains the emission spectra of elements, and for a single electron system, the math of the Bohr model works beautifully. But of course, we have some problems with the Bohr model as well. The Bohr model doesn't explain the shape of molecules. Obviously, the math is a huge problem. But also fundamentally, the Bohr model just says electrons are in orbitals, because it doesn't have any real explanation as to why an electron can only be in n equals 1 or n equals 3, and there is no n equals 2.5 ever. So enter a few gentlemen, one of whom I'm sure you've heard of, Albert Einstein. In 1905 is working on something called the photoelectric effect. And that's where light is able to knock electrons off of a metal electrode surface. And this is really weird because light, after all, is a wave. It's an electromagnetic wave traveling through space. But in order for it to be able to push on a particle, then Einstein says that light is also a particle of energy, a little packet of energy that he calls a photon. This is wave-particle duality. It's one of the fundamental things about quantum mechanics physics. And Einstein says that this only works when electrons get pushed by an energetic enough packet or photon of energy. So Einstein says that light is both a wave and a particle. It depends on the situation. De Broglie asks the converse question. If light can be a wave and a particle, can a particle also act like a wave? And in fact, they find that this is the case. Matter can have the properties of a wave. And you can in fact calculate the wavelength of this particle wave. And it involves Planck's constant, which is very, very tiny, divided by very tiny mass times a very big volume. So you get a tiny number divided by an even tinier number, which means you get a really tiny number. And electrons then can act like very tiny light waves. In fact, this is the basis of scanning electron and transmission electron microscopy, where you get some really famous, beautiful images like the one of the inside folds, the cristae, in a mitochondria. That is a transmission electron micrograph. The electron waves are so incredibly tiny that they can interact with structures that are too tiny for the light that we can see. But it really doesn't explain how electrons stay in one place. And in order to do that, we're going to think about the types of waves that you can have. You can have a traveling wave, like a sound wave or a light wave, but you can also have what's called a standing wave. And I have a little video here of a standing wave demonstration. And a standing wave is going to look pretty much exactly like this. You'll see when we start. We spin up the string, and when enough energy gets into the string, it sets up this standing wave. It really doesn't look like it's moving at all. It just seems to be standing in one place. So this is a standing wave. What I want you to pay attention to is in a minute they're going to start varying the speed of this motor. And can you see that not every possible speed sets up a standing wave? Some of them just give you a bunch of wiggly junk, and then you find the right energy and you'll see it snap into that standing wave again for just a second until they change the energy again and it goes away. So particular energy levels can set up a standing wave. So looking at a little standing wave anatomy, a standing wave has to have a whole number of lobes, or what's called antinodes. Or to phrase it a little differently, it must begin and end at a node. So you can have one antinode or lobe with two, or you can have the entire wavelength. This, remember, we measure from crest to crest for a wavelength, and that would require having two lobes and three nodes, one in the middle here. This is a node. And if I put even more energy in, I can make a more complex standing wave that has three antinodes. And you saw in the demonstration that when they had a bunch of lobes and nodes on the wave, it had that motor spinning really, really fast. So the more energy there is, the more complex the wave will be. But you can never have half a wave or half a lobe. So one thing I like to do is I like to draw the little, looks like a 8-year-old draws a goldfish. And then I put a big old universal no on it. No, you cannot set up a standing wave that looks like this. It has to begin and end at a node. So any of the speeds in between here and here didn't work. Only that particular energy did. Which, if you start thinking about it, might explain a problem we've been having. Because electrons can only be found at certain specific energy levels. Never a little bit out, never in the middle. Ooh. So in the quantum mechanical model of the atom, the electron is pictured as a standing wave, a three-dimensional standing wave. So the shapes are much more complex, or can be much more complex, because they're in 3D. That principal quantum number n indicates the energy. So n equals 1, n equals 2, n equals 3. That's the energy level of that wave. And now all of a sudden we've got some interesting things because we have some explanations for the Bohr model that we didn't have before. Why are electrons only in specific energy levels? Well, because those are the energy levels that allow a standing wave to form. Why can it only absorb specific energies? Because it has to go from one standing wave to the other. It can't be between because you can't have a wave there. The energies that are not exactly matched to the gaps between the waves pass through and aren't absorbed, and therefore would also not be emitted in an emission spectra. And the other thing we say is that this is also possible because energy is quantized. It comes in chunks, individual photons of light or energy. And a quanta is the amount of energy that allows movement from one energy level to another. And since you can't have the wave and you can't have the energy between, there's a leap in energy. So once this theory was proposed and understood, Schrödinger derives an equation which describes the energy and position of electrons in an atom, the Schrödinger equation. And thank goodness you don't have to try and solve it. The Schrödinger equation is designed to mathematically describe what's going on with the electron in the vicinity of the nucleus. It's a parametric equation. So you set up specific quantum number, specific limits unique to each region of space that the electron can inhabit. It's three-dimensional, and it relates three quantum numbers. So it kind of comes in three pieces. And that corresponds to the quantum numbers, which we're not going to go over quantum numbers because we did it in first year. And I'm sure there's a There's a really nice description in your textbook, and I would suggest looking at it. But the principal quantum number is the shell. That's the n equals 1, n equals 2, n equals 3. Then inside that shell, there are specific orbitals that are possible according to the math. And so that is going to be given to you by your orbital quantum number. And m sub L is which one of the orbitals are you going to find? Some subshells or orbitals have multiple possible orbitals. And so m sub L is going to kind of narrow that down even further. It's kind of like saying you're at Johnson, you're in the E wing, you're in E217. Each one of these parameters narrows down the location of the electron. And these are interpreted and drawn as basically a 90% probability. There's a 90% probability if I point at that shape, I should be able to find an electron. And we'll look at those shapes and types more in our next video.